Welcome. In this video, we look at section 6.2, Sum and Product Rules for Probability. This is day one, and we will begin by looking at the birthday problem, which is a famous problem, and that can be solved with the techniques of section 6.1. And then the main topics of this lesson are the sum rule and the product rule. Let's get started. The birthday problem. This is a classic probability question. What is the probability that some two people in this room have the same birthday? Well, the way we can figure this out is 1 minus the probability that all birthdays are distinct. So let's say that we're in a room of 30 people. So in this room of 30 people, what's the probability that some two people have the same birthday? It probably doesn't seem that likely, does it? I mean, after all, there's 365 different birthdays, ignoring leap year, and there's only 30 people in the room, but let's find out what the actual answer is. So I want to figure out 1 minus the probability that all the birthdays are distinct. Well, the probability that all the birthdays are distinct is 365 per mute 30 divided by 365 to the 30th power. So 1 minus that number ends up being about 0.71 or 71%. And that's surprising to most people. The fact that in a room of 30 people, you'd have a 71% chance that some two people have the same birthday. It turns out that when you get to 23 people in a room, that's the moment when it just tips over 50%. In fact, here's a little graph I found online. You can see the number of people in the room. That's what's on the bottom. And then the percent likelihood that two or more people share the same birthday is graphed vertically. And this is pretty amazing, right? Once you get up around 55, 60 people in a room, it is almost certain that some two people have the same birthday. So there it is, the power of probability, and all done with the kind of mathematics we studied in 6.1. Moving on to 6.2, we're going to take a close look at two fundamental ideas, the sum rule and the product rule. We begin with the sum rule. Here's our definition. Two events are disjoint, or mutually exclusive, if they cannot both occur simultaneously. For example, let's say we roll a pair of dice. Event 1 might be at least 1 3 appears, and event 2 might be the sum is 10. Well, these both can't happen at the same time, because if event 1 occurs, at least 1 3 appears, then the biggest that the other die could be is 6, right? So the biggest that the sum could be is 9. So we can't have a sum of 10. Here are three examples, three pairs. Take a moment, pause the video, and for each pair, see if you can decide whether these events are disjoint or not. All right, give it a try, and then start the video again to check your work. Let's take a look. In the first example, we toss a coin 4 times. Event 1, exactly 3 heads appear. Event 2, exactly 2 heads appear. No, you can't have exactly 3 and exactly 2 at the same time. So yes, these are disjoint events. Second example, choose 2 cards from a deck. Event 1, the cards have the same value. Event 2, the cards have the same suit. These are disjoint because suppose that event 1 occurs. The cards have the same value. So maybe one card is a 4 and the other card is a 4. Well, they'd have to be different suits. So maybe one is a heart and the other one is a club. There we go, my little drawing of a club. Right, I can't have a 4 of heart and a 4 of hearts because there's only one 4 of hearts. And similarly, if I had drawn 2 cards that were the same suit, say I drew a diamond and another diamond, well, can't have the same number, so the two values would have to be different. So yes, these two events are disjoint. In the third example, make a 3-person committee from 8 men and 12 women. Event 1, the committee has a woman. Event 2, the committee has a man. No, these are not disjoint events because the committee could have both a man and a woman. Here is the sum rule. The sum rule says that if event 1 and event 2 are disjoint, then the probability of event 1 or event 2 is the probability of event 1 plus the probability of event 2. So it's a really nice rule. It's very easy to apply, but it's also very important that our hypothesis is satisfied. This sum rule only works if the two events are disjoint, if they are mutually exclusive. Let's see an example. Suppose we roll 2 dice. Event 1, at least one die is a 5. Event 2, the sum of the dice is 5. When I think about these two events, I might make my sample space of 36 possible outcomes, like this 6x6 grid here. Maybe the outcome of die 1 on the left and the outcome of die 2 up above on the top. And maybe event 1, I can indicate that with a check mark. So I've checked all the outcomes that satisfy event 1. And then event 2, I'll put a little X in those outcomes. Are these two events disjoint? Yes, I can see that because there's no overlap between the two sets. And so to compute the probability that event 1 or event 2 occurs, it's just the probability of event 1 plus the probability of event 2. There are 11 check marks and there are 4 X's, and so 11/36 plus 4/36, and our answer is 5/12. But here's the more general form, the general sum rule, because things are often not disjoint. Here we go. If event 1 and event 2 are any two events, then the probability of event 1 or event 2 is the probability of event 1 plus the probability of event 2 minus the probability that they both occur. We've seen something like this before when studying sets. Do you remember? Let's say I have my sets E1 and E2, because after all, E1 and E2 really are sets. And I consider the union of these two things, E1 union E2. And I might want to know how many elements are in the union of those two sets. Well, how I figure that out is by taking the number of elements in E1 plus the number of elements in E2 and subtracting the number of elements in E1 and E2. Oh, but now look at this. What if I divide both sides by the size of the sample space? There. Well, that's exactly what I have on the right side of the equation up above. And so there it is. There's our proof of the general sum rule. Let's do an example with the general sum rule. So we roll 2 dice. Event 1, at least one die is 5. Event 2, the sum of the dice is 8. What do these events look like now? So event 1 is the same as before. I marked those off with check marks. Event 2 is a little bit different. Here, the X's show those outcomes where the sum of the dice is 8. And you can see there are 2 possible outcomes where there's overlap. These 2 places that I've circled, this is where event 1 and event 2 are both satisfied. At least one die is 5, and the sum of the dice is 8. So now, well, first of all, are these disjoint events? No, they are not. There is overlap. So if I want to compute the probability of E1 or E2, I start like before. I compute the probability of E1 plus the probability of E2, and then I have to subtract off the probability of E1 and E2. So I'm subtracting off those 2 instances, the 2 out of 36. And so we have 7/18. There we go, 7/18 as our answer, which is really what you were wondering about, weren't you? Now you are a better person for knowing the answer to this question. Okay, give this thing a try on your own. What is the probability that 3 cards chosen from a standard deck of cards consists of either 3 face cards, that is, cards having a value of Jack, Queen, or King, or 3 cards of the same suit? In the example here, the 3 cards happen to be increasing 3, 4, 5, but they don't have to be. They can be any 3 cards of the same suit. Give this a couple minutes, see what you can do, and then start the video again to check your work. All right, let's take a look. To begin, let's count the number of ways that these things can happen. In this first case, how many ways can I have 3 face cards? There are 12 face cards altogether. So the number of ways that I can make a set of 3 face cards is 12, choose 3. And then on the right, how about the cards that have the same suit? Well, a suit has 13 cards, and so within a suit, I have 13 choose 3 ways to pick my 3 cards. And there are 4 suits, so this guy needs to be multiplied times 4. Now, there is some overlap. there are some cards that satisfy both of these. So in fact, what about the face cards that are all of the same suit? I can have Jack, Queen, King of spades, or Jack, Queen, King of clubs, or I can have those cards in hearts, or I can have those cards in diamonds. So in fact, I think there are 4 possibilities. So I've counted them, but now let's turn them into probabilities, because after all, I'm choosing these cards, these 3 cards, from the entire deck. So in the first case, what's the probability that I choose those 3 face cards? It's 12 choose 3 out of 52 choose 3. And in the second case, out of 52 choose 3. And in the third case, out of 52 choose 3. So finally, I'm almost at the end now. What will I do to compute my answer? I'll take the first answer on the top left plus the second answer, the one on the top right, minus the third. And that should give me the solution. And so in fact, there it is. All of that ends up being about 0.0615, so about 6%. The product rule. Here's our second big idea. And previously, like I had a definition of disjoint that was important, in this case, I have a definition for the word independent, which will be important for us. 2 events are called independent if the occurrence of one event is not influenced by the occurrence or non-occurrence of the other event. For example, suppose you roll a pair of dice, one is red, one is green. Event 1, the green die is 4. Event 2, the red die is 6. The red die. Does the red die care at all what the outcome of the green die is? No, the red die does not care. The probability that event 2 occurs is not influenced at all by the outcome of the green die. These are totally independent events. There's an old riddle that if you flip a coin 100 times, you flip a fair coin 100 times, and it just by some freak of nature, it just happens to be heads every time. What's the probability that on the 101st throw, it will be heads also? And the answer is 50-50, because flips of a coin are all independent. It doesn't matter what happened before. Every flip is independent of the one that came before. Here are some more examples. Let's see if these events are independent. Say you roll a die 4 times. Event 1, the first 2 rolls sum to 7. Event 2, the last 2 rolls sum to 10. Yes, these are independent. The outcome of the first 2 rolls has no influence on the outcome of the last 2 rolls. How about this one? Choose 2 cards from a deck. Event 1, the cards have the same value. Event 2, the cards have the same suit. Do you think these are independent? These are not independent, because if the cards have the same suit, then the cards can't have the same value. So the outcome of the first plays a big role in determining whether the second happens or not. Third example. You make a 3-person committee from 8 men and 12 women. Event 1, the committee has a woman. Event 2, the committee has a man. So does the occurrence or non-occurrence of event 1 influence event 2? In fact, it does. So these are not independent events. It turns out that the probability of E2 by itself is approximately 0.81. But if you know that event 1 has actually happened, if you know that the committee has a woman, then the probability that the committee has a man goes down just a little bit. It goes down to about 0.80. One way to think about that is that if the committee does have a woman, then we've lost the possibility that the committee has all 3 of them being men. So, at any rate, there is a slight influence, and these 2 events are not independent. With the definition of independent now under our belt, let's turn to the product rule. Theorem 3, the product rule. If event 1 and event 2 are independent events, then the probability of event 1 and event 2 is the probability of event 1 times the probability of event 2. For example, let's suppose we roll a die 4 times. Event 1 is the event that the first 2 rolls sum to 7, and event 2 is the event that the last 2 rolls sum to 10. The probability of event 1 and event 2 both occurring is the probability of event 1 times the probability of event 2, which turns out to be 6 out of 36 times 3 out of 36, which is 1 out of 72. So there is our probability. This product rule should look kind of similar to the sum rule, the first one we had. With the sum rule, the basic one, if event 1 and event 2 were disjoint, then the probability of E1 or E2 was the probability of E1 plus the probability of E2. And so there's kind of a similar look, right? And what we did with the sum rule was that we found a generalization. And we'll do the same thing with the product rule, but that is a topic for another video. So this is where we stop.